Alright, so we've got this scenario. We're at a 7-Up production facility, and the quality control engineer is worried that the filling machine is miscalibrated. In other words, she wants to make sure the machine is not under or overfilling the cans. Now, I want you to think for a second. Even if, say, the machine was underfilling cans, does that mean the standard deviation is too low? No, what we mean by underfilling is that there's not enough volume in the can, or that the volume is too far below the mean. That means the variation is high. So we're still talking about sigma being very high there, or greater than the 3.2 that it should be, right? And certainly this is apparent if we were talking about overfilling the cans. So that's why if the machine was out of calibration, then the standard deviation is too high. So we're going to test the claim that the population standard deviation, sigma, is greater than the 3.2 milliliters that it should be. So in other words, the null hypothesis is that sigma is equal to the 3.2 milliliters that it should be. The operating assumption would be the machine is properly calibrated. And the alternative is the claim that the machine is miscalibrated, which would be that the standard deviation is higher than the 3.2 milliliters it should be. And this is important because, if you're overfilling bottles, you're wasting money. If you're underfilling bottles, you're going to get sued or you're going to get hit with government fines because you're not providing what you claim to provide. So that makes this a right-tailed test. So that's the first step in the process, is identify the test you're doing, and then step 2 is identify the level of significance of your test, which we said alpha was equal to 0.05. The third step in the process then is to get my chi-squared test statistic. Now remember, my chi-squared test statistic is equal to n minus 1 times s squared over sigma squared. So you're going to want to take a second here, go back and calculate s squared from those 9 data values. So calculate the sample variance of those 9 data values. So my chi-squared test statistic for this is the 9 data values minus 1, so that's my degrees of freedom here. The sample standard deviation is 3.464. rounded to 3 decimal places, and I rounded to 3 decimal places because my chi-square test statistic I want to 3 decimal places, so for precision's sake that's what we're doing. And then this is over, don't forget that's squared. And by the way, you could have calculated the variance, the sample variance for that, which is 12, which is 3.464 squared. And that's over sigma squared, which sigma was supposed to be 3.2, remember. So sigma squared. And if we punch that into our calculators, we come up with a chi-squared test statistic of 9.374. Since this is a right-tailed test, I want to know the probability of a chi-squared value being greater than my test statistic, So we can do it using the p-value or the classical approach, but we'll go ahead and use the p-value approach. So we want the probability that a chi-squared value would be greater than my test statistic, which was 9.374. So I'm going to use technology to do that. And so what I'm going to do is I'm going to use a TI-84. You can use Excel. It has chi-squared distributions on it. But I'm going to call up my chi-squared CDF, my chi-squared cumulative density function from the distributions menu, and it takes a lower bound and an upper bound, so we want from 9.374 to infinity with degrees of freedom. So remember there were 9 data values, so 8 degrees of freedom. And if I execute that, I find that the probability, or my p-value, is equal to 0.3117. right? Or not that unlikely, right? So now that I have a p-value, I can make my decision, right? So my p-value is significantly greater than alpha. That means that my particular data set was not that rare, right? And assuming that the population standard deviation actually is the proper 3.2 milliliters. So this is telling me to fail to reject H naught, right? Or in other words, I didn't see anything that out of the ordinary, assuming that the population standard deviation actually is the proper 3.2 milliliters. So in other words, there was insufficient evidence to conclude that the population standard deviation is actually higher than it should be. Or let me write that out for you. And the meat of what we want to understand is that right, the meaning is that the equipment does not appear to be miscalibrated, right? That's the whole point of conducting the test. We came up with this phrase, oh, okay, sigma, there's insufficient evidence to conclude that sigma is greater than 3.2, but what that means is the equipment is essentially, appears to still be correctly calibrated. So there is an example for you of calculating a hypothesis test concerning a population standard deviation.